Hi, sir. Hello. Good morning to all. This is Ramakrishna, Senior Manager, Inovine Conferences. Thank you for joining online conference on chemistry and nanoscience. This is the second day of the conference. Thank you for attending chemistry experts and nanoscience experts and healthcare experts. Uh, Mr. The first keynote session, Dr. Anil Ramdas Bari. He is working in Department of Physics, Arts, Commerce and Science College, Badwad, Maharashtra, India. Sir, Anil sir, shall you please share your screen before
Hello,
we start the presentation?
can you hear me?
Yes, sir. Yes, sir.
Yes, sir. Thank you, sir, for nice introduction. Can I start my presentation?
Yes, sir. Yes, sir.
Okay, let me share screen. My screen is visible.
No, sir. Yes, sir. Yes, right.
Hello.
Yeah, yes, sir. Ready. Yes, sir. Visible.
My screen is visible, sir.
Yes, sir. Yes, sir. Visible. Ready.
Okay. Thank you,
Yeah.
dear friends. Celebrating its 72 second Republic Day in this year. Republic Day is celebrated every year in India on January 26 to commemorate the date on which the Constitution of India came into effect in the year 1950 and the country became a republic. On this occasion, I wish all the researchers gathering on this online platform for a very happy Republic Day. Now, I am delivering my keynote speech on preparation of nanostructured ZNO powder and its use as a thick film chemical sensor. Myself, Professor Dr. Aniram Dasbari, Head and Assistant Professor, Department of Physics, Arts, Commerce, and Science College, Bodwad, which is affiliated to Kavitri Bainabai Chaudhary Now, the outline of my presentation is 1 minute. Introduction, preparation of nanostructures Jadona powder, characterizations, fabrication of thick film sensor, sensing performance, and finally the conclusions. We know that there are two types of gases. We have converted it into conventional gases and simulant of chemical warfare agents, which is known as CWAs. So in this present investigation or study, we have worked on these two types of gases, that is conventional gases and simulants of chemical warfare agents. The conventional gases includes ammonia, which produces the lung diseases, irritation, and other. Carbon dioxide, it produces feel discomforts and develop nausea and headaches. Chlorine, it is irritating eyes and respiratory system. Ethanol produces hypotonic and depressing activity in the upper brain. Hydrogen produces high concentration, causes oxygen deficiency, headache, and ringing in the ears of vomiting. Liquid petroleum gas, which is highly inflammable and exposure of which causes the difficult breathing and accident may cause the burning. While the chemical warfare agents and any chemical which through its chemical effects on the living process may cause death, temporary loss of performance, or permanent injury an animal. These chemical warfare agents are liquid, aerosol, or vapor. It is highly toxic. It is highly toxic, not too difficult to handle, capable of being stored after a long period in the container without degradation and corroding, resistance to the atmospheric water and oxygen. It withstand the heat developed when dispersed. Now we can see the history of that chemical warfare. In 1915, chemical war occurred during the World War I, where German forces released 160 tons of chlorine gas and killed 5,000 soldiers. In 1915 to 1918, World War I, where German and British forces used 1,13,000 tons of chlorine, mustard gas, and for 2,000 to 1 million people. In 1925, Geneva Protocol banned using the. In 1913 to 1940, open car shooting. World War II, screenshot didn't use biological or chemical war, but Germans developed the chemical nerve agents sarin, tabun, and soman. In 1917, during the Vietnam War, US used defoliantants. In 1995, sarin gas released into the Tokyo subway, that is a system, killed 12 people and injured over 5,500 people in 16 nations. WhatsApp मध्ये 2001 to 2010, anthrax in New York, pesticides in China, chlorine in Afghanistan, killed 2,250 to 3,000 was injured. In 2012 to 2015, rat poisons, pesticides, multiple chemical agents, sarin mustard gas, and chlorine in Afghanistan, Syria, Iraq, 405,000 injured and 1,630 were killed. So how dangerous? We can see that history, that how dangerous this chemical wars were. Now these chemical warfare agents is classified into various classes. First one is nerve agents, which includes tabun, sarin, soman, psychosarin, VX, novochic agents, choking agents, which includes chlorotonic, chlorine, phosgene, diphosgene, while blister agents, which includes sulfur mustards, nitrogen mustards, lewisite, phosgene, oxamine, also things that contain ricin and herbine, while the industrial toxic agents, which includes hydrogen cyanide, nitrous oxide, carbon monoxide, hydrogen chloride, methyl isocyanide, mercury, lead, benzene, hexachlorides, 1,3,5 trichlorobenzene, dichloromethane, chloroform. Now we can see the routes of entry and symptoms of that agents. First one is choking agents. Its routes of entry is inhalation. It produces the symptoms of burning of nose, mouth with rhinothoria, respiratory districtness with coughing fits, with weakness, headache, while the nerve agents, which includes uh, attacks the nervous system by affecting the transmission of impulses. Routes of entry, inhalation, and through the skin, while the symptoms increase the production of saliva, runny nose, and feeling of discomfortness. What is the feeling of pressure in the nervous system? While the blister agents, which is also called as vesicants, its routes of entry is readily absorbed by all part of that body, and its symptoms is general destructionist of the tissues and inflammation, also the blisters. Now you can see the actual photograph of that inflammation and blisters on the skin of human due to these blister agents, that is the vesicants. Okay. Now, in while during the chemical wars, these are the photograph showing the chemicals wars in the atmosphere. This is the actual photograph of that atmosphere that contains the chemical wars. This is the chemical wars. While during the operation, such type of troops are required, which have the all types of facilities to protect the soldiers from that chemicals wars. And third one is, this is the actual photographs of the troops during that operation while the chemical wars are released in the atmosphere. Now, we didn't use chemical wars actually in our laboratory because it is highly toxic and not to handle, or it is handled too difficult. We use the simulant of that highly toxic chemical warfare. So we use the simulant of serine, that is dimethyl phosphonate, then 2-chloroethyl phenyl sulfide and 2-chloroethyl ethyl sulfide, the two simulants of that distilled musters. Now, how this gas or what can affect these gases and chemical wars? It affects the global warming, ozone layer depletion, acid rains, health problem, chemical wars, and damage the environmental property. Hence, it is necessary to detect and control the hazardous gases in the atmosphere. For this purpose, the semiconductor metal oxides, generally zinc oxide, tin oxide, tungsten oxide, titanium oxide, barium titanium oxide, barium oxide, indium trioxide, etc., can be used as a sensor material. And why these sensors are needed? It is to detect and control the pollutants in the environment in the form of gas or moistures, to minimize the health hazards, to avoid the hazards of the global warming, and to avoid the curious episode. So sensors is needed. Now what is the sensors? The sensor is a device that receives the signal or stimulus and responds with an electrical, electronic, or optical signal. It is called a sensor. Where these sensors can be used, that is the user sectors of the sensors, that is environmental protections and pollution control unit, office automation, industrial control and automation, vehicle exhaust detection, security alarm in the industries as well as banks and houses. How these sensors can be prepared? There are three types of sensor technology. First one is thin film technology, which is used the different thin film preparation techniques. Thick film technology, that is the screen printing technique. And third one is pallet. It requires dye, hydraulic press, and the material of which pallets is to be made. So these are the technologies, sensor technology. In the present investigation, we work on the zinc oxide, that is the sensing material is a ZNO, zinc oxide. This is a crystal structure of that zinc oxide having rutuzite structures, and these are the properties of that zinc oxide having the its value and other properties also. Now experimental, we can use the ultrasonic atomization technique to prepare the nanostructured zinc oxide powder. This is the actual photograph of that ultrasonic atomization technique, and this is a schematic diagram of that ultrasonic atomization technique. This technique include the ultrasonic generator. This is an ultrasonic generator which include the piezoelectric transducer. There is 3 piezoelectric transducer. This is a liquid tank. This is a 2-zone furnace, one first zone, second zone, and this is a trapping system. We can trap the nanostructured, prepared nanostructured powder in this trapping system. This is a solution preparation and optimized parameter. That is the first zone. We can maintain the temperature of 150 degrees centigrade. That is the drying zone temperature. And second zone temperature is 1000 degrees centigrade. That is the pyrolysis zone temperature. Now, appropriate molarity. That is the molarity of zinc nitrate solution were poured into this liquid tank. This liquid tank slowly deliver this solution into the ultrasonic atomizer. This atomizer consists of piezoelectric transducer. This transducer converts the solution into that fine mesh. So this solution can be converted in fine mesh. This mesh can be pushed forward with the help of this oxygen or air cylinder, and it is put into the first zone temperature or the first furnace. We can say that the first furnace. So the temperature of the first zone is 150 degrees centigrade. It is remove the water from that mist. Only the dust particle is there. Then this particle can be pushed forward on the second zone temperature. This second zone temperature is near about 100 degrees centigrade, which convert this fine mist into the oxide nanoparticle. That is the zinc oxide nanoparticles, and these particles were collected into the different number of tracks. These traps is novel because it can sort the size wise particle of that nano powder. So bigger size is here, then smaller, then smaller, then smaller, then smaller. So we can use this smaller one size for our preparation of the thick films. Then we can characterize this powder with the help of Xray diffractogram. This is a Xray diffractogram of a typical zinc oxide or prepared zinc oxide nanopowder, and having the crystal structure is about rutuzite and size is about 18 nanometers. We can calculate the Debye-Scherrer formula size by using Debye-Scherrer formula, and the broadening of the peak shows that the prepared nano powder should be the nanocrystalline in nature, so it is 18 nanometer in size. Then this powder is further characterized, or we can say that surface morphology with the help of SEM, microstructure with the help of TEM, and electron diffraction pattern with the help of EDS image. From the surface morphology, the particle size is observed to be 30 nanometer, having agglomerated particles, and shape should be the spherical one. Then from transmission electron microscopy, the crystalline size should be 20 nanometers, having spherical in shape. And in electron diffraction pattern shows the crystalline nature of the prepared nanostructure powder. Then this powder again further characterized with the help of elemental composition. The theoretical expected mass percent of that zinc and oxygen in stoichiometric proportion of that ZNO are expected to be 18.3 and 19.7 respectively. The observed value of mass percent of ZNO represented in table this, that is 18.34 for the stoichiometric, and this is 18.7 and 13.15. So it is clear from the table that the prepared zetone powder was observed stoichiometric. Near to their stoichiometric proportion, we can observe that elemental composition. Now, this is a fabrication of the thick film sensor using screen printing technique, which is simple. We can prepare this powder, thick film, with the help of laboratory. This is a simple screen printing technique, and this is a schematic diagram of that screen printing technique. The thiotropic paste were formulated by mixing the lab paper nanostructure zinc oxide powder with the solution of ethyl cellulose, which is called as temporary binder, and a mixture of organic solvent such as butyl cellulose, butyl carbitable acetate, and terpineol. This ratio of the inorganic to organic part was kept to 75 to 20% in the formulating the paste. So this is a simple screen printing technique. Now these are the sensors prepared in our laboratory. We can prepare our sensor on the glass substrate. These are the various type of sensors prepared in laboratory. By using other sensors in the present investigation, we can use these thick film screen sensor, thick film sensor for the present. Now this is a sensing system to test the simulant as well as the gases. This is the actual photographs, indigenous gas sensing system present in our laboratory at Department of Physics, Nanomaterials Research Laboratory, Department of Physics, Pratap College, Amalner. And this is a schematic diagram. This includes the supply, then temperature indicator. This is the insulator where there is a heater to heat the sensor. This is the actual sensor. We can build this sensor here. This is a thermocouple to measure the temperature, and this is the gas inlet. We can expose the gas, and this is the temperature where we can measure the volt as well as current of that sensor specification. Now, what is the measures of that sensor? That is the important measures. There are four types of important measurement we can do on the sensors. First one is response, selectivity, response, and recovery time. So response is defined as the ratio of the change in conductance of the sensor on the exposure of the target gas, or we can say that the still simulants on the original conductance in air, and is given by the relation S is equal to Ig minus I upon I, where Ia is conductance of the sensor in air, Ig is conductance of the sensor as a target gas or simulant. Now selectivity is defined as the ability of the sensor to respond to certain gas simulants in the presence of the other gas, while the time taken for the sensor to attain 90% of the maximum increase in the conductance on the exposure of the target gas or simulant is known as response time, while the time taken by the sensor to get back 90% of the maximum conductance when the flow of the gas or the simulant is switched off is known as recovery time. So this is the important measures of the sensors. Now, this is the actual sensing performance of the conventional gas as well as simulant of the gas. So in the first graph, we shows the operating temperature versus gas response. Of that, exposed gases were LPG, CO2, H2, NH3, chlorine, and ethanol. Among all the gases, the most sensitive gas were observed to be ammonia at an concentration of 1000 ppm at an operating temperature of 300 degree, giving maximum response to 17.30. And this is the second graph shows the sensing performance of that simulants. We can expose DMMP, CEES, and CEPS gases onto that sensor. The most sensitive simulants were observed to be DMMP. Concentration is 2 ppm at an operating temperature of 450 degrees centigrade, giving maximum response is 4.31. Look at that ppm, that is the concentration is only 2%. 2 ppm is there. So highly toxic that simulants and chemical markers are there. Now, selectivity among all the gases, the conventional gas, that is ammonia, is selective in comparison to all the gases at 300 degrees centigrade, given maximum response 17.3, while among CWS and CPS, this DMMP is a selective simulant of that nanostructure zinc oxide thick film. Now, the response time and recovery time of that conventional gas. The first figure shows that the response and recovery profile of that ammonia gas. The response time is 17 seconds and recovery time is 35 seconds. While the second graph shows the response and recovery time of chemical warfare, that is the DMMP simulants, which gives the response time is 15 seconds and recovery time is 45 seconds. Now, finally, conclusions. The XRD analysis confirmed that the powder to be of ZNO with rutozite structure. Same image showed roughly spherical particles with average size of 30 nanometers. Average grain size calculated from XRD is 18 nanometers, and from 10 it was observed to be 20 nanometers. The response of nano thick film sensor was observed to be largest to the ammonia at 300 degrees centigrade. It shows quick response 70 seconds and fast recovery 37 seconds for ammonia. The response of nanostructured thick film sensors to the DMMP at 400 degrees centigrade was larger than other simulants, while the quick response 3 seconds and fast recovery 7 seconds were the important features of the nanostructured sensors. So the nanostructured could be a promising candidate as a sensor for detecting the conventional gas and simulants of that chemical warfare agents. Finally, I am very much thankful to the University Grant Commission, New Delhi, India, for the financial supports for this work from the Department of Information Technology, Defense of Research Development Organization, Government of India, New Delhi, Head Department of Physics and Principal, Pratap College, Ammaner, India, for providing the laboratory facilities for this work. Also, my college, principal of my college, and also I'm very much thankful to the organizer for giving me the chance as a keynote speaker of this conference. And this is some of the publications which is published in Sensor and Actuator B Chemicals, Advanced Powder Technology, Materials Science and Engineering B, Sensor and Actuator B Chemicals, Current Applied Physics, IEEE Sensors. These are some snapshot of that my publications. Maximally, most of the publications were done in the Sensor and Actuator B Chemicals. So thank you very much.
Thank you, sir, for nice presentation, sir. And any doubts, all of the participants? Hello. Please ask Mr. Dr. Anil Bar is clarified all your queries, doubts. Nice presentation, sir. It's a wonderful presentation.
Okay,
And
thank you, sir.
Thank you for joining our Inovine conferences. And we will meet you in physical event in the future.
Oh, yes, sir. Yes, sir. Definitely. If anyone have any problem, please feel to ask.
Yes.
So I can give you the answer. Whatever the problems is there.
I will share the Dr. Bari email ID to all your attendees. Any queries, please mail to Dr. Anil Bari. Thank you, sir. Thank you very much for the wonderful presentation. And next, one second. The next presentation, Dr. Suji Wakta, Nagoya Institute of Technology, Japan. And Dr. Suji Wakta.
Yes, I'm ready.
Yes, sir.
Yeah.
The title of the speech, Large-Scale Computer Simulations about the Stability and Adhesion of Metal-Organic Interfaces.
I'm Shuji Ogata from Nagoya Institute of Technology. Today I'm talking about large-scale computer simulation about the stability and adhesion of metal-organic interfaces. Let me start from the motivation. Adhesive bonding. This is a key technology in automobile manufacturers. So they are seeking for a lightweight materials body. So for that purposes, they need reliable bonding technologies for various body materials such as lightweight aluminum. And then this figure is a trend of the predicted trend of the joining processes. Well, presently 2021, something around here. Then still a majority is at the resistance spot welding. This is very old-fashioned style method. But gradually, and in 10 years, adhesive bonding take over this kind of old-fashioned style. So there is a strong motivation that we can perform the theoretical analysis of the adhesive bonding method. So of course there exists a theoretical study or seminal theoretical study of the adhesive strength. This is done by the Japanese group here. Then they prepare the gamma aluminum because gamma aluminum is mimic the surface aluminum oxide. Then they put the X molecule model here. Then they got the curve or the Hall speed curve, something like this. Then ideas adhesive strength by the derivative of this one is 300 megapascal, but in experiment only 30 megapascal. Then that means that more than 20 times difference, huge difference exists. Because of that, we want to have the much more realistic analysis in theoretically. So but the system is very challenging because that you want to take care about the large system size of the polymers. Then we have the various part of the inhomogeneity, and then of course the chemical reactions occurs in some part. So that means that we want to address the large computer system. Then of course accuracy is a DFT level. So much computation time is necessary. So our idea is that we use supercomputer. Recently one is Fugaku in Japan to perform the large-scale accurate simulations. Then we address from two directions. One direction is that we use reaction dynamics by using the QMMM hybrid method. In this method, we apply the electroshock calculation only to a limited regions. Then the other approach is we use the thermodynamic analysis by the DFT based thermodynamic integration to get the free energy of each theoretical state and the calculations and chemical bonding breaking barrier energies. Then we use two methods to address the industry important problem of the weakening of the interface bonding by moistures through computer simulation and calculations. This is the first part, hybrid computer simulation. So the epoxy molecules we use is shown here. Then this is called a bisphenol A epoxy molecules. You have the epoxy group here, and the ethyl group here, and the hydroxide group here. Three functional group of the interest for us. And then we have repetition number n. So n ranges from 0 to 20 according to the experiment. Then of course the large n questions are large viscosity. Then we need a curing agent to make a bridging of these epoxy molecules, something like this. Then we have the curing agent here, and 5 epoxy molecules and bridged together. Then some epoxy group still remains. Then according to the experiment, 10% or 30% of this group remained unreacted as the interfaces. So because of this, we use two extreme models for the hybrid simulation. One model is that the 100% group still remains. The other model is the 0% group remains. So this is a model we use. For the n equals 0 model, we focus on the effective groups. Still, epoxy group exists, the two end. The n equals 0. The n equals 1k model, we focus on the hydroxide group here. Then 2n epoxy group is replaced by the CH3. And we use such two models to produce interface. we have in the case n equals 0 cases, we have the aluminum here, aluminum oxide, surface oxide, and the epoxy resin. Then epoxy resin is produced by 36 times some of the Xy molecules entangled. In the n equal 1 case, we have the large size compared to the n equal 0, so we have to prepare a large system size compared to the n equal 0. Then this red region is taken care by the quantum mechanical ways, or the DFT, using the DFT method. So this is the overview of what we do using the hybrid quantum classical simulation. So this right end region is fixed, atomic position is fixed, and this left end region of aluminum is gradually shifted at constant speed of this much to the lower minus directions to get the stress on the resin. Then we monitor the stress rate on the resin and can get the maximum value of the stress. This corresponds to the maximum adhesion strength of this system. Then, because we use a hybrid method, this central, this green region is taken care by the DFT, electron level simulation computation method. Then this left and right end region, two regions are taken care by the classical way. I mean that the classical driving force field is applied to the resin regions. The aluminum region here, this can be taken care by the classical ES plus variable charge potentials. This is famous for that can replace the pure aluminum and also amorphous aluminum oxide. Then this green region is taken care by the DFT. Then our idea is that we insert water molecules in between the surface aluminum and also between the epoxy resin, and these regions water molecules inserted. Then get the ideas of chemical reactions. Then because the large system you have to take care by the DFT, about more than 1,000 or 1,500. Then that means that we need efficient code, computation code on the supercomputers. So we have our original DFT code, then based on the real space grid DFT. Then if we have a molecule something like this, the overlapping grid point is set up on the computer. Then each grid point have the data about the eigenfunctions and the potential field. Then this, because the real space grid, this is free from the atomic basis and easy to be used to other systems also. Then, but still order n-cube method. But anyway, by the way, that the final difference means that we use several number of the grid point to get the Laplacian values. Anyway, so still this is an n-cube method. Then we have the additional feature recently that the divide conquer idea is used to get the order n method. So in this case, this model, for example, divided into two domains. Each domain is much smaller number of the grid point. Then, if we have many computation facility, number of computation CPUs, we apply for the domain 1, domain 2 differently, independently, and then we get the faster computation in total. Then, because of this kind of abrupt termination of the grid point, we need additional artificial potentials from the conscious communication. This term we call embedded and density potential. This artificial potential have the two laws. One law is that this enforces the continuity of the electron density at the domain boundaries. Another law is that shifting some artificial levels, because of the existence of the abrupt termination of the grid point, artificial surface states emerges. Then energy level is tuned to get the original states. So this is the idea. This left end region of the aluminum is gradually shifted, and then we have some stress field here. So this is the main results of the computer simulation results. So we have this in the left side, we have the data for the n equals 0 simulation. The right data corresponds to the any one cases. Then in each left and right, we have 4 cases of simulation, 4 cases of the setting. Case 1, we have no water inserted at the interface. Case 2 and 3, we have little bit some number of water molecules inserted at the interface. In the case 4, we have much water inserted. Then in this case, in this n equals 0 cases, case 1, maximum shear stress is about 300. Then this value is much 10 times larger than the experimental value. Experimental value of the maximum stress is 30 megapascal, and which decreases by 30% in the existence of moisture, but 10 times larger. But in the computer simulation results, existence of moisture make the lower the maximum shear stress about half. That means still 100 to 150 is the value of the maximum stress, even after the insertion of the water molecules. Then this is unrealistic because of the too large composite experiment. In the right-hand data, shear maximum, we have the 3 cases here. We have no water in the black case. Maximum value is 50, and then going to 0. And less water cases, we have the almost the same maximum value of 50, and then going to 0, and again going to 50, and then 0, and again something, this kind of zigzag behaviors, fluctuation. The case C, much water cases, we have basically no stress felt on the resins. So basically this value is 50. This is compares very well with experimental value 30 megapascals. But a little bit through the detail, what is happening in this kind of zigzag behaviors. Basically, what we found is that adhesion strength of the less water and the no water cases is 50 megapascal. This is in good agreement with experiment. Experiment is 30 megapascal. Then, in that sense, this is a realistic model. Then, in the ordering of the adhesion strength, is less water is much larger than the much water cases. But why this kind of large fluctuation of the stress occurs in the less water case? This is the reason of shear what is happening in the case B. In the case of n equal 1, in the case n equal 1, if this kind of hydroxide group here, then this oxygen have some small amount of the hydrogen bonding between the unsaturated surface aluminum, because this is amorphous surface oxide. Then this oxygen goes to here, then this hydrogen terminate the oxygen, then this hydrogen going to the other aluminum. So this kind of exchange reaction occurs in the case B. Then the barrier energy is only 0.1 electron. This small barrier is because of the 2 aluminum and the hydrogen on the amorphous surface oxide assist this kind of reactions. Then this was observed in the 2 places here. Because of that, abrupt release of the stress occurs 2 times here and here. That was the reason. So this I was just talking about case B. Then if we have no water, then simply hydrogen is subtracted to the surface aluminum. After the subtraction, because the repulsion between oxygen and oxygen, stress epoxy group feels almost no stress coming from the aluminum side. Then we have much water inserted in the interface because of the existence of the OH ions. Then OH ion attack the epoxy molecules, then break the bond. Then this is also occurring 2 times. Now coming to the part 2, free energy calculation and the barrier energy of the chemical. So this is the idea of the curing. We have here 5 times epoxy molecules, then curing agent, mixture of this, because the amino and the epoxy group make a reactions like this. Opening of the epoxy group, oxygen, and the hydrogen simply changing the positions. Then hydroxide is produced here, and then this is a bridging. So in this case, 5 wings, and then N1, N2, and N3 atoms here, this amine. Then remember that NH3 in water, much percentage of the NH3 can change to the NH4 plus. This is ammonia water. So N1, N2, N3 can have the possibility to be protonized or deprotonized depending on the situation in waters. This we are talking about. So we can calculate this kind of free energies using the method of the Sulpizi at ETA about 10 years ago. Then we have the half reaction, something like this. Then calculate this free energy independently, and then combining together, we get this total free energy of the protonation, deprotonation reactions in water. Then we can calculate using a DFT by using the thermodynamic integration method. Eta degree corresponds to a degree of deprotonation. Then we have performed this kind of simulation using a DFT, molecular dynamics simulation of artificial Hamiltonian depending on the eta. And then here deprotonated means that the zero Coulomb energy of the dummy proton. Then we can get this kind of delta. Then what we did is that a little bit shortened cured epoxy molecules inserted in the water molecular system. Then we calculated this data. In N1, N2, free energy is a little bit different. N1 minus negative values, N2 is positive. That means that this protonized state is stable in N1. N2, proton is subtracted to the water because of the, as this figure shows that in N2 cases, this is the distribution of the hydrogen of H, NH, and O of H2O. Water molecules can come very close to the this amine. So water molecules subtract the hydrogen ions. So let's think about the possibility of weakening of the chemical bond by the existence of protonation and the existence of the H2 molecule. Then I'm trying to talk about this amine group reaction and also this ethyl group reaction in the existence of the two effects. So in the dry condition, we have no water here. In this case, this is the reference data. CO bond breaking barrier energy is 2.86 electron volt. This is the barrier energy state, breaking this here. And in the case of CN bond of the amine group here, in this case, because the hydrogen protonated amine, not protonated. This is a dry steel condition. In this case, amine group is 2.30 electron volt. Then after the reaction, coming back to the epoxy group after the breaking. Then if we have the wet condition, in this case, CO bond breaking is assisted by the breaking of H2O, something like this. The barrier energy becomes 2.30. This is much smaller compared to the dry station. The CN bond breaking. That in this case, protonated amine group exists. That means that only 1.94 electron volt. This is the lowest barrier energy of breaking a bond of the cured epoxy molecules in water. So that means that the substantial lowering of bond breaking of barrier energies occurred by the protonated effect. So this is a summary of our present study. For the first part, we have performed the hybrid QMCL simulation of the reaction dynamics. Then we get the adhesion strength between the aluminum resin and the surface oxide aluminum agrees with the experiment. And also the adhesion strength weakens due to the moisture in agreement with the experiment. Additionally, we found that the chemical reactions, this is various kinds of chemical reactions that involve the aluminum atoms of the surface aluminum surface oxide and epoxy molecules are found. The part B, this is for the free energy calculation of the cured epoxy resin in wet conditions and also in dry conditions. Then we have found that in one of the three amine groups, protonated state is stable. So because of that, in wet conditions, barrier energies for the ethyl group and the amine group substantially becomes lower in wet conditions. Then this enhances the breaking of the cured epoxy resin in wet conditions. So thank you very much for your attention. Thank you.
Thank you, sir.
Yeah.
Thank you. Nice presentation. And any questions, Dr. Suji Okta? Any questions to Dr. Suji? Thank you very much, sir, for presentation.
Thank you very much.
Event.
Yes.
On
Yes.
behalf of OCM of Chemistry Congress 2021, we want to thank you for insight presentation.
Thanks.
And looking forward to meet you again in next time.
Yeah. Thank you very much for the organizer. Yes.
Thank you, sir. Now we ask Dr. Sabu Thomas. He is Vice Chancellor and Professor Mahatma Gandhi University, India, to join the event and start the presentation. Dr. Sabu. Dr. Sabu Thomas.
Can I start?
Yes, sir. Yes, please start.
Yeah. The title of presentation is Engineering at the Nanoscale: A Strategy for Developing High-Performance Functional Materials. Sabu Thomas, Mahatma Gandhi University, Kottayam. So I'm going to talk about a series of materials, clay and polymer composites, that its application in tire engineering, CNT polymer systems, hybrid systems, super tough materials for space, and bio-nano composites. So my group is quite active in a variety of nanomaterials, graphene, CNTs, variety of nanosystems we are active. Nanosilica, zinc oxide, nanocellulose. So what we really do is, let us look at this, the clay system. We've been very active in clay, putting clay into polymer systems. I will show you some of our work on clay. So this is a polymer system, this is clay. If you do a very good mixing, you can get beautifully exfoliated system. If the mixing is bad, you end up in a sort of conventional composite. This is something intermediate, it's an intermediate situation. So my group is very active in making a very strong polymer interface, where we do different things, surfactants, block copolymers, variety of systems we apply. We do a lot of chemical modification of the clay. We make use of surfactants, compatibilizing agents. We make use of amino acids, alkylamines, polyetheramines, silanes to connect polymer and the clay surface. Most of the polymers are hydrophobic. Clay is hydrophilic. So this is our strategy. This is clay, is hydrophilic, and interact with a compatibilizing agent. Here is a tetraalkyl ammonium compound. And then you see tetraalkyl ammonium compound get into the intergalleries and the gallery space is increased. And when you do that, you see how do you follow this? It's a very interesting slide. Look at this is a neat clay. Very small gallery spacing. This is a neat clay. Look at this. When you put different types of surfactants into the clay, you see the gallery spacing is shifted to lower angles, or this peak is shifted to lower angles. That means you increase the gallery spacing. This is what we do. My PhD students always do this. Collect clay, react to the surfactants, and increase the gallery spacing. Then the polymer can mix extremely well. I will show you one example. I had a brilliant student from France. She came to my laboratory. She made excellent nanocomposite. We published in Langmuir some day back. You see, she made use of clay, and we did two types of manufacturing. One with surfactant. Look at this. This is a surfactant molecule. Another one without surfactants. When we polymerized the aniline on the surface of clay without surfactant, you know what we got? We got an interconnected system. And the mechanics were very poor. Conductivity was lower. But when we did a surfactant modification, then polymerization of aniline, you know what we got? We got a fantastic nanocomposite, excellent nanocomposite. We applied this in tire engineering. I'll show you a couple of slides. See, look at the air permeability. Natural rubber has a very high level of air permeability. But you put 5% of bentonite or a fluorohydride, you see the permeability is dramatically decreased. Very dramatic reduction in permeability. Okay, I can show you how we organize the clay platelets. This is natural rubber. You see, we have organized the clay platelets beautifully. Let me show you some of our work on multi-wall carbon nanotube. You can see our collaborators and PhD students. We put multi-wall carbon nanotube into rubber. And we also used a beautiful coupling agent, ionic liquid. This is the ionic liquid. Ionic liquid can connect is BR rubber and carbon nanotube. When we use ionic liquid, you see carbon nanotube is beautifully dispersed in the polymer matrix. If you don't use any ionic liquid, you have lots of agglomeration. Look at this. And you can see this type of percolation we got. This is a concentration of multi-wall carbon nanotube in PHR, in its BR rubber. See, after 2.5 or 3, we got a beautiful percolation process. You know what we did ultimately? We made soft elastomers for EMI shielding. We made conductive composite, which is very flexible, which is very soft. And we made soft elastomeric materials for EMI shielding. Let me show you another example. We had a very strong cooperation with General Cables United States. A PhD student of mine, Josephine P. Joss, she made use of different types of nanofilters. You see, we mixed the clay. This is XLP matrix with aluminum oxide. You see a lot of clusters. We could not disperse aluminum oxide in XLP matrix. We put clay. Clay got a reasonable dispersion, 5% of clay. You know what we did? We mixed clay and aluminum oxide and put into XLP. You know what happened? The XLP clusters have been destroyed and we got a beautiful network formation. You can see this is clay, this is aluminum oxide. Look at this. You got a fantastic self-assembly process when we mix two nanofilters together and we put into the polymer matrix. Look at the mechanics we got. This is neat XLP, 263 megapascals. 5% of clay, 370. 5% of aluminum oxide, 384. Look at this combination, 2.5, 2.5, 812. Big jump. So we have shown to the company that if you mix two nanofilters intelligently with proper surface modification, you can get fantastic properties. Let me show you our work on with ISRO, Department of Space of India. Department of Space gave a mandate. You know, they have been using epoxy resin for a variety of applications. It's a fantastic material. The problem of the epoxy is the impact is poor. The fracture resistance is poor. The crack propagation is so fast. So what we did is we mixed epoxy resin with the block components of different molecule weights, different composition, And if you blend them intelligently, you can make cortical, you can make spherical mesocyl, we can make worm-like structures, we can make vesicles. I will show you just a couple of slides. A PhD student of mine mixed epoxy resin with styrene, butadiene, styrene triblock copolymer, where the butadiene part has been epoxidized. When we do that, look at the nanostructures we have developed. We have developed beautiful nanostructures, very nice nanostructures. And that gave rise to good impact modification. This is a cartoon of the structures we have made. This is a polystyrene which doesn't like epoxy, forms a sort of core. And the shell is epoxidized butadiene. And then you can see the cross-linked epoxy. Let me show you some of our biomedical applications. My group is very active in biomedical applications. You can see my co-workers, postdocs. We do a lot of electrospinning, PCL, PLA, polymer blends, and we make non-woven scaffolding material. You see? And if you examine this under electron microscope, we get a beautiful nanostructure. Then we made wounds, sacrificial wound. Wound has been closed by this tape. You see, after a couple of weeks, complete healing of the wound. We also did a lot of in vivo studies with guinea pigs. You can see we have made the wound and the wound has been closed. This is the internal structure of our tape, highly porous. We also added, nanoparticles to accelerate the healing process. For example, zinc oxide we added, just 1%, 50 nanometer size. Excellent effect on wound healing. Because zinc oxide can react with oxygen forming hydrogen peroxide. That is actually giving lots of interesting results. Cell proliferation, excellent cell migration, excellent wound healing, and angiogenesis. We have also made, we also looked at the degradation process. You see, after a while, your scaffold should disappear. This is 5th day, 10th day, 20th day. Look at this. If you put 1%, this is PCL, neat PCL. This is neat PCL with 1% of zinc oxide. If you put a little bit of zinc oxide, the dual advantage. The wound healing is fast, and also after a couple of weeks, the degradation is fast because eventually the scaffolds have to degrade. Look at the quantified wound healing process, number of days, and wound healing efficiency. The best one was PCL with the 1% of zinc oxide. You can see this is 1% of zinc oxide. You see the hair growth. If you don't use zinc oxide, only PCL, you don't see much of hair growth. And you see the positive and negative samples. So this is the best, PCL with 1% of zinc oxide. We are also into nanomaterials from agricultural waste. We extract a lot of nanomaterials from agricultural waste. I have a big group in this area. I will show you a couple of slides. This nanocellulose is very beautiful material for photonics, in composites, in medicine, in modification, in Phillips and forms. It's a fantastic material. See, if you look at the father of bio-nanomaterial, I would say Alan Dufresne from Grenoble. He has done wonderful work. He made beautiful nanostructures from biological waste, munition cellulose, wheat straw, crab shell. You know what we have done? My PhD student made nanocellulose from banana stalk. He went to the banana plantation, collected the banana stalk, and made nanocellulose in my laboratory. So this is nanocellulose suspension in water. He injected aniline into it. And then we went for a polymerization process. Very simple reaction. Then he went for vacuum filtration, hot pressing. You know what he made ultimately? Conducting thin nanocellulose paper. The surface of which you have polymerized aniline polyaniline is extremely conductive. And this was a fantastic material for EMI shielding. We were able to make nanocellulose of 1 mm thick, 0.5 mm thick, a fantastic material for your mobile phone as a EMI shielder, lightweight. Following this procedure, another PhD student of mine, he did the same protocol. And then, you know what he did? He went for freeze drying. He made forms. His paper is published in Carbohydrate Polymers. He made beautiful forms. The same protocol, same material, but he made forms. And he also got excellent EMI shielding, something like 20 or 25 I mean, 30. We went up to 30 with certain treatment. You see, 30 shielding efficiency. And finally, what I want to say, this is my concluding remark. My group is very active, making nanocomposites for functional applications, nanocomposites for tire engineering, for barrier, nanocomposites for cable applications, nanocomposites for EMI shielding, nanocomposites for electrical connectivity, nanocomposites for biomedical applications. Let me thank all my funding agencies, DST Nano Mission, thanks to Professor Sena Rao for the generous funding. Professor Rao has supported us quite a lot. All the funding agencies in the country and abroad, industrial funding, General Cable United States, Surface Street Check, Apollo Tires, MRF Tires, my collaborators worldwide, France, Germany, Brazil, Belgium, and many, many thanks to my students. I really presented the results of my students. They did a lot of hard work. You can see my group in chemistry. My collaborator from France, this is my group in chemistry, chemical sciences. This is me. And you can see our group in Nano. We have a very big group in Nano. Now the present director is Professor Nanda Kumar. He became the vice chancellor of the university. He's directing the Nano group. And this is our campus. Very welcome to the campus after the pandemic. We have a beautiful campus. Some photographs of Kottayam, Corson country. And we have very old temples. We have beautiful canals, houseboat, Kathakali, the dance of young girls. I'm the editor of nanostructures and nano objects. So to those who are interested, those who work on nanoscience, please submit your article to nanostructures and nano objects. Size score is now 5.6, no fee. It's a traditional journal, no pay charges. We had celebrated a beautiful conference in November, 100 years of macromolecular science. This was last year. We are organizing a meeting in April 9, 10, 11, online meeting on nanomaterials. So I request everyone to attend this conference, online meeting. So thank you very much for your patient hearing. And thank you and very welcome to your campus after the pandemic. Thank you. Any questions, please?
Any questions? Any questions too? Any questions? Dr. Sabu Thomas. Thank you very much, sir, for presenting in this event. On behalf of the organizing committee member of the Chemistry Congress 2021, we want to thank you for insight presentation. Looking forward to meet you again next time, if everything goes well in physical event.
Thank you for the fantastic meeting.
Thank you very much, sir. It was a nice presentation.
Thank you.
Yes. Now we ask Dr. Vakthanga Barbagdes from Tbilisi State Medical University Institute of Pharmacochemistry to join the event and start presentation.
Hello, dear moderator.
Yes, sir, you can start your presentation.
Is it okay? Is it visible, my presentation? Is it okay? Do you see my?
Yes, sir. Just you can start your presentation. Sir, we are unable to audible your voice.
So, no success? Oh, do you see my presentation? Oh, no.
Yes, we can.
You can see?
Yes, yes.
Can I start?
Yes.
Okay, okay. Greetings, everybody. First of all, I would like to express my gratitude to organizing committee for invitation, which gives me opportunity to do this presentation. So, subject matter, title of my presentation is polysugar acids, natural poly-3,3,4-dihydroxyphenyl glyceric acid, its synthetic analogs, and their anti-cancer effect. I am Dr. Vakhtang Barbakadze from Tbilisi State Medical University, Institute of Pharmacochemistry. Subject matter of our research for a long time was isolation and structure elucidation of polysaccharides from medicinal plants and investigation their biological activity. We investigated different species, high polysaccharides of different species of some plant families. Family Laurantaceae, family Liliaceae, family Grassulaceae, family Crassulaceae, family Amaryllidaceae, family Cucurbitaceae, family Iridaceae, family Taxaceae, and the most interesting results we got among the species of family Boraginaceae. Is it good visible of PPT presentation or no?
Yes, it's fine, sir.
It's okay. Yes.
Yes.
Okay. Let me to show you nice pictures of some plants from some plants of Boraginaceae, Symphytum asperum, prickly or rough comfrey, Symphytum caucasicum, Cocosian comfrey, Cocosian endemic, Symphytum officinale, common comfrey, Symphytum grandiflorum, creeping comfrey, Georgian endemic, Anchusa italica, Italian Baglas, Cynoglossum officinale, hound's tongue, and Borago officinale, borage or common borage. This is scheme of isolation of high molecular fraction from above mentioned medicinal plants. By this scheme, we got crude polysaccharide preparation which showed high anti-complementary immunomodulatory activity and antioxidant activity. It motivates us to find the active principle of these crude polysaccharides. For this purpose, we did ultrafiltration on membrane filter with cutoff value 1000 kDa and obtained high molecular preparation. This is the following absorption maxima at 282, 286 nanometer were observed in ultraviolet spectrum of high molecular fractions from above mentioned medicinal plants. This is infrared spectrum of high molecular preparation, which contain absorption bands characteristic of phenyl carboxylic acids. And for structure elucidation, we use the different techniques of NMR spectroscopy, C13 NMR, H1 NMR, attached proton test NMR, two-dimensional heteronuclear H1, C13, HSQC, NMR, and analyzed data of different techniques of NMR in this table. In this table, according to this table, we established structure of main chemical constituent of a high molecular preparation, and this is poly 3,3,4-dihydroxyphenyl glyceric acid. This is regular polymer, and the repeating unit of this polymer is 3,3,4-dihydroxyphenyl glyceric acid residue. This biopolymer, the chain, the polyoxylene chain is the polyoxyethylene chain is the backbone of this biopolymer, and carboxyl acids and dihydroxyphenyl residues are a regular substituent in the chain. On the other hand, this biopolymer we can imagine as exotic new class, a rare class of polysaccharides. So in this case, poly-2,3-glyceric acid ether chain is the backbone of this polymer molecule, and the dihydroxyphenyl residues are a regular substituent at this in this chain. Thus, according to data of different techniques of NMR spectroscopy, C13 NMR, HH proton test, H1 NMR, 1D NOE, and 2D H1 C13 HSQC, the main chemical constituent of high molecular preparation from Symphytum asperum, Symphytum caucasicum, Symphytum officinalis, Cyanoglossum officinalis, and Borago officinalis is polyoxy 1-carboxy 2,3,4-dihydroxyphenyl ethylene, or poly 3,3,4-dihydroxyphenyl glyceric acid. On the one hand, the polyoxylene chain is the backbone of this biopolymer, and the 3,4-dihydroxyphenyl and carboxyl groups are regular substitute at 2 carbon atoms in the chain. The repeating unit of this regular polymer is 3,4-dihydroxyphenylglyceric acid residue. So structural unit of this biopolymer is the simplest sugar oxidative form of glyceric acid, which is oxidative form of simplest sugar, aldotriose glyceraldehyde. So biopolymer from symphytum from Chusa italica and Borago officinale and Symphytum grandiflorum had methylated form of carboxylic groups. This signal in C13 NMR is methoxyl signal. And in H1 NMR, methyl ester signal is a signal which with chemical shift 3.8 ppm. And this is two-dimensional heteronuclear HSQC spectrum, and this cross peak is signal of methoxyl group, correlation between hydrogen and carbon atom. This is in this table is the total assignments of signals in the C13 and H1 NMR spectra of high molecular biopolymer, and we did total assignment of the signal. 70% of carboxyl group are methylated. This is the 2D dose experiment of this biopolymer. No substantial differences of diffusion coefficient. Both sets of the signals fell in the same horizontal. This is signal in Symphytum asperum polymer spectrum, and this signal not seen in Symphytum asperum polymer spectrum. So thus the similar diffusion coefficient for the methylated and non-methylated signals of this biopolymer is observed. Both sets of signals fell in the same horizontal. This would imply a similar molecular weight of methylated and non-methylated polymers. Thus, the NMR signals of both methylated and non-methylated carboxyl groups originate from the same poly 3,3,4-dihydroxyphenylglyceric acid polymer. In order to confirm the proposed structure of the repeating unit of non-methylated and mostly methylated in carboxylic groups of these poorly water-soluble high molecular weight substances, the C13 solid state NMR spectra were recorded. The methyl carbon of the ester group shows a broad signal at around 72 ppm, as indicated by arrow. Total assignment of the signal of solid state C13 NMR of biopolymer and the methylated biopolymer are in good agreement with the results of above mentioned liquid state C13 NMR classical spectra of biopolymer and methylated biopolymer samples in heavy water. This biopolymer has a wide spectrum of biological activity. This biopolymer is multifunctional. It contains one carboxy group and two phenolic dihydroxyphenyl groups. And due to this multifunctionality, it should be a reason of wide spectrum of biological activity of this biopolymer. It exhibits anti-complementary activity, antioxidant activity, wound and burn healing activity, and anti-cancer activity against prostate cancer cells. Then we synthesized monomer of this biopolymer using asymmetric dihydroxylation of transcaffeic acid derivative using a potassium osmoate catalyst. Like this, we got racemic monomer and two enantiomers of this biopolymer. The biosynthesis of the rather rare class of natural polyethers that belongs this biopolymer has not been known, but from the chemical viewpoint, this process can be conceived as the epoxidation of double bond in caffeic acid, followed by the ring opening polymerization of the resulting epoxide. Then we try to get epoxide, which is epoxide as a starting compound for further polymerization by ring opening polymerization, and to get synthetic analog of natural polymer. Afterwards, methylated epoxide of starting compound, epoxide of starting compounds using a cationic initiator, boron fluoro 3 etherate. We got by ring opening polymerization methylated derivative of natural polymer. Structure of synthetic methylated analog we elucidated by different techniques of NMR spectroscopy and Malditov mass spectrometry. This is unit of this synthetic methylated polymer, and there are theoretical mass and observed mass. Later, we tried to do green chemistry, ring opening polymerization of starting compound using enzymatic polymerization and the protection. We used as enzyme from Candida rugosa, and the size exclusion chromatography and the Malditov analysis showed the formation of oligomers with degree of polymerization up to 5. It should be mentioned that enzymatic polymerization is a green chemistry alternative to classic chemical synthesis, as it utilizes processes that minimize the use and the generation of hazardous substances. That is why it is the method of preference for the synthesis of biologically active natural polyether analogs. This is size exclusion chromatography heliograms. This is Malditov mass spectrum of obtained oligomers. Then we investigated the in vitro and in vivo experiment anti-cancer activity of novel phytochemical poly-3,3,4-dihydroxyphenylglyceric acid, zibrocolon, and its synthetic monomer, white columns. And both compounds suppressed the growth and induced death in prostate cancer cells 22RV1 and LCAP with comparatively lesser cytotoxicity. Zebro and white columns towards non-neoplastic human prostate epithelial PWR1E cells. Thus, our new biopolymer and its synthetic monomer selectively inhibit growth and induce death in human prostate cancer cells. Molecular studies suggested that this biopolymer, zebro columns, and its synthetic monomer, white columns, caused G1 arrest in prostate cancer cells through modulating the expression of cell cycle regulators, especially an increase in cyclin-dependent kinase inhibitor, P21 and P27. Thus, biopolymer under study, zebro column, and synthetic monomer induce cell cycle arrest by modulating cell cycle regulatory molecules in human prostate cancer cells. This slide shows effect of synthetic biopolymer, natural biopolymer, natural polymer and its synthetic monomer on apoptosis, zebro column and the white columns in human prostate cancer cells. These compounds induced apoptotic death in prostate cancer cells by activating caspases C3 and caspase C9, and also strongly decreased androgen receptor and prostate-specific antigen, PSA. This slide shows effect of natural polymer oral administration of human prostate cancer 20RV1 tumors and secreted prostate-specific antigen in anemic nude mice. 22RV1 cells were injected subcutaneously on the right flank of each male anemic nude mouse, and the biopolymer 5 milligram per kilogram body weight was administered through oral gavage route 5 days a week for 5 weeks. After 5 weeks, the tumor volume per mouse was decreased by 88%. Control versus and the plasma analysis revealed that biopolymer administration at 5 milligram per kilogram doses caused a strong dose-dependent decrease in prostate-specific antigen level by 87% compared to control. Together, these results clearly showed that anti-prostate cancer efficacy of biopolymer in vivo. And in this diagram, you can see that prostate-specific antigen concentration was decreased 5 times. So, conclusion. The first representative of a new class of natural polyethers regular caffeic acid-derived polymer or novel polysaccharide, namely poly-3,3,4-dihydroxyphenyl glyceric acid or polyoxy-1-carboxy-2,3,4-dihydroxyphenyl ethylene, has been isolated from species of Symphytum, Anchusa, Cyanoglossum, and the Borago, Boraginaceae family. Most of the carboxyl group, 70% of Anchusa italica, Symphytum grandiflorum, and Borago officinalis are methylated. The racemic and enantioselective synthesis of a novel glyceric acid derivative, the monomer of PDGA, as well as its anti-cancer efficacy against prostate cancer, is described. Ring opening cationic polymerization of a 2,3-disubstituted oxyrane derivative to methoxycarbonyl 3,3,4-dimethoxyphenyl oxyrane afforded to a methylated biopolymer. By green chemistry, enzymatic ring opening polymerization of oxyrane, methyl 3,3,4-dibenzyloxyphenyl glycidate using lipase from Candida rugosa, and further the protection afforded to a mixture of oligomers of biopolymer with degree of polymerization of up to 5. Preclinical investigation revealed the strong efficacy of biopolymer against prostate cancer cells and identifies this polymer as a potent agent against prostate cancer without any toxicity, and supports its clinical applications, suggesting high potential in prostate cancer patients. So, acknowledgements. And thank you for your attention.
Any questions?
Okay, thank you very much.
Yes, any questions to Dr. Vakhtang?
Okay.
I think no more questions.
It
Yes.
is bad connection now.
Any questions to Dr. Vakhtang? If you have any questions, just you can text in chat box. We'll be asking behalf of you. So, okay, thank you very much, sir. Thank you very much for speaking.
Okay, thank you for your attention.
Yes, thank you very
And
much.
thank you very much for your invitation to take part in your nice conference. Thanks a lot.
Thank you very much for
Okay, thank you.
meeting and providing a unique perspective. Thank you for sharing your tips with us. Looking forward to meet you again next time. Now we ask Dr. Rory Waterman from University of Vermont Department of Chemistry from USA to start the presentation.
All right, I can do that. I'm just going to take a second to get my screen sharing. Good morning, everyone. It's very early in Vermont, so it's good to be here. Thank you very much for the invitation. Let's get this on the road. All right. And then is that visible? Come on, let's get that presentation. All right, and then I'll give myself a pointer too. Okay, great. As was said, I'm Roy Waterman. I'm from the University of Vermont. I'm happy to tell you a little bit about hydrophosphonation catalysis. Clearly, this is a very diverse event. There's a lot of different kinds of chemistry, and so my plan is to share a broader overview of what we do and not delve too deep into the very specific aspects of the chemistry. This is a shot of my research group in beautiful Vermont. Clearly, this is before COVID because nobody's wearing masks and we're all quite close, but it is nice to see some faces. Primarily the work of Steve Dannenberg. More recently, Brian Novas has been a significant contributor to the story that I'll tell you today. So a little context, we do some things other than hydrophosphonation, but hydrophosphonation is the story. For now, in general, we think about very simple chemical reactions to build bonds in the main group. So simple sigma and pi bonds in systems, really like silophosphines or diphosphines, these fundamental molecular structures. And the reason is that these molecules are already important. So organic chemists use silophosphines to deliver a phosphide reagent, or diphosphines are interesting because they can be constructed into long chain emissive polymers, for example. And across the main group, there are, a myriad of examples of these kinds of molecules from, groups 13 through 17. And the reality of the main group chemistry in the P block is that it is fairly synthetically limited by comparison to traditional organic chemistry. And there's a lot of interesting reasons for that. But when you have a stoichiometrically based synthetic economy, then you lose efficiencies in the kinds of molecules you can make, the reactions you can do. That also leads to higher wastes and costs in processing. And these are already important molecules. So in our thinking, the best option to improve this is to use catalysis. And so in general, our efforts are focused on building new synthetic methodologies that lead us to new molecular precursors or value-added molecules. And of course, we want to learn actually just how these bond-making processes work. So for this particular time, I'll tell you about hydrophosphonation catalysis, the simple addition of a pH bond across an unsaturated substrate. And generally, these reactions do not need to be catalyzed depending upon the nature of the unsaturated substrate. A catalyst adds generally selectivity and reactivity, and so that's a big issue. So the purpose of doing this is really to improve this particular reaction that doesn't necessarily need a catalyst. And so the challenges in hydrophosphonation in a general sense are with substrates, because the reaction does need the catalyst to avail substrate use. And then, of course, where are a lot of improvements that can be made over pre-existing catalysts. I want to step back from that hydrophosphonation story for a minute to talk about phosphorus in general. Phosphorus is an element that has some issues with it. And so when, the non-chemical population, at least where I am, think about phosphorus, they're often thinking about phosphate. And phosphate pollution is runoff. And so down the bottom corner, I show actually a picture of an algae bloom in Vermont in Muscoit Bay from a few years ago. And so this is sort of the worst case scenario of phosphorus pollution. These lead to a lot of interesting chemical issues. These are places where chemists can contribute quite readily in thinking about how to measure phosphorus in the environment and how to help manage it, clean it up, but really the fundamental problem with phosphorus is availability. This is now a fairly dated diagram, but if anything, it's only a little bit more accurate if it was to be replotted. Our total phosphate reserves are finite on the planet, of course, and our use of phosphorus is largely non-recycled. And so ultimately there will be a peak in phosphorus and phosphorus utilization. And so that's a challenging question for society, is what are we going to do with this resource that is ultimately finite if we continue to put most of it back into the ocean? And it's not, of course, phosphorus alone. Phosphorus is one of many elements that we're struggling to have a sufficient amount of in the future. And so this is a wonderful diagram that illustrates the limited availability of a variety of elements. And some of these, of course, are new strains related to, for example, electronics versus older, longer pressures on, for example, helium. Most of phosphorus, of course, is used in agriculture, and so I very much simplify the process by which we get phosphates for agricultural use, which is most commonly through the wet process, the sulfuric acid processing of phosphate ores into various precursor phosphates with additions of amines to make amine derivatives. And so almost 90% of what is phosphate ore out of the ground goes to making phosphate that ends up in the agricultural industry. So this is by far the most significant use of phosphorus, but that differential 10 to 12% of non-agricultural phosphorus goes to a wide range of applications. And so just to sort of bookend those, on one side, we can think about molecular compounds, and this is Fosprin, which is a blood pressure control medication. And so clearly phosphorus being at the center of this thing and very structurally important illustrates how even in small amounts we can dramatically influence bioactivity. To the other end in materials and thinking about solid state materials like semiconductor ceramics, such as gallium phosphide, which are prevalent in LEDs and other materials, advanced materials of that regard. So going from those two extremes, there's a lot of potential demand on phosphorus in that limited space that we use it for non-agricultural purposes. So it's clearly up to us to create methodologies that utilize this finite resource to its maximum efficiency. Our guiding plan, of course, follows green chemistry principles. It was illustrated or alluded to a few moments ago very nicely. And so in particular, we're thinking about catalysis, but the 6 items that are up there I've highlighted are the ones that we tend to be thinking about as we work through what we do. And on that then note, what I'll tell you is that the story today is thinking about efficient use of phosphorus through catalysis. These are 3 particular reactions that we've been exploring specifically in my lab for a lot of years. One of these is alpha phosphinidine elimination, or the extrusion of a low valent, formerly phosphorus 1 fragment of phosphinidine from primary phosphines with a metal-based catalyst to do phosphorus carbon bond forming reactions. And so that's not the focus today, but it is something that we are very interested in. Another one is a uniquely main group reaction, dehydrocoupling. So we can take 2 phosphine substrates and with a metal catalyst eliminate hydrogen to form a phosphorus-phosphorus bond. And then the last reaction, the one the subject today, is the addition of a pH bond, of course, across an unsaturated substrate, or hydrophosphonation. So the hydrophosphonation story, it has really developed a great deal thinking about photochemistry and photocatalysis and photoactivation. And that's what I think is really a game changer, and it's going to drive the reaction for the next 5 years or so. And it really starts with not doing a particularly good job of hydrophosphonating substrates. And by saying that, I'm openly admitting that when we were starting out, we were not targeting hydrophosphonation, and we were looking at really just the fundamental organometallic chemistry of the zirconium phosphido compound that we had identified now several years ago. And as organometallic chemists do, when we often produce new molecular species, we explore small molecule activations, because small molecule activations are very informative. If we do a reaction and we see the reactivity we anticipate, then presumably we understand the compound. And if we see a unique reaction, then there's something to be explored in detail. At this point, we were doing insertion reactions at the zirconium phosphorus bond. Those were successful. And so those model insertion reactions led us to think that perhaps we could engage in hydrophosphonation catalysis. And so using this compound, the zirconium phosphido derivative, as catalyst, we were able to successfully hydrophosphonate terminal, generally aryl, but terminal alkynes to give vinyl phosphines. We had some selectivity in the product, although not great selectivity in the product. And we were easily able to extend that chemistry to hydroarsenation as well. The conditions were not great. The catalyst loading was relatively high. The temperature was relatively high. It worked, but it was unimpressive. At that time, we started to explore other substrates, and we were finding that we were significantly limited in that we were only successful with terminal alkynes. And that was a fairly vexing observation. It was unclear why we were seeing that. except through observation of the catalysis. And during the catalytic reaction itself, we were seeing conversion between the added catalyst, the terminal phosphido compound, and a terminal alkynyl derivative. And at that time, we wondered if, in fact, the reason we were only seeing activation of terminal alkynyl substrates for the catalysis was that the zirconium was serving to make this more amenable to a direct addition from the phosphorus, from the phosphine. And in fact, there was no insertion-based hydrophosphonation catalysis. So for all of those reasons, we thought that this was not a great reaction to continue to explore. And really all we wanted to do was, at that point, was measure the equilibrium constant between those two metal-based compounds in solution to sort of wrap up what we were doing. And as one would do, we simply set up the left side of the reaction and the right side of the reaction, hoping to get to the same distribution of products and then therefore be able to accurately measure a KEQ. So I'll show you the right side of the reaction first. So the alkynyl compound plus phosphine gave no apparent reaction. And that was a confusing observation initially. We knew something had to happen because there was catalytic chemistry that we were not observing at that time. And so scratching our heads a bit, we decided that a useful step would be to actually deuterate the phosphine to see what would happen at that point. And upon deuteration and reaction, what we saw was complete consumption of the deuterium from phosphorus and formation of the phosphine, the proteophosphine. All of the deuterium ended up on the trimethylsilyl substituents of the zirconium. And this was due to a cyclometallation event that we had been identifying separately for this compound. And so pH activation was opening a silyazometallacyclobutane intermediate. So there was chemical reactivity here. There was exchange of deuterium. There was no apparent net reaction simply because the stable derivative was the terminal alkynyl compound and not the phosphido. So we were seeing actually that the equilibrium should lie heavily to the right. Of course, we did do the left reaction at the same time as well, stoichiometrically, and so terminal phosphido compound, terminal alkyne, therefore gave primarily terminal alkynyl compound, as I've indicated it should. However, there was a competing process by which we were forming, or which we were retaining the phosphido derivative, because in fact there was some competitive insertion and a small amount of that vinyl phosphine product was formed. So these were not really a full study on the mechanism, but we had enough information to draw a decent proposed catalytic cycle for this, which would be the phosphido derivative undergoing a 2-1 insertion to give the vinyl phosphine intermediate, and product liberation was by that key CH bond activation at the trimethylsilyl substituent that I alluded to a minute ago to give the silyazometallacyclobutane that I mentioned. This compound, which we can isolate independently, we know rapidly activates pH bonds to restore phosphido compounds. It also directly activates the CH bond of a terminal alkyne to make a terminal alkynyl derivative. The reason we were seeing the alkynyl compound was an equilibrium process that heavily favors the alkynyl compound. But of course, as we were forming any concentration of the phosphido, we gave the possibility for insertion. And so the catalysis would turn over, but we were in fact substrate inhibited. So the substrate inhibition was a challenge for doing further catalysis with this particular compound. And at that point, which was, I don't know, maybe 8 years ago. So I'm going back, and actually 10 years ago, I'm going back in time a bit. It gave us pause, and we said, hydrophosphonation is not a great reaction with these triamide-amine zirconium compounds. We should stop doing it. And so we did. And until there was an excellent discovery. And I mentioned dehydrocoupling. It's not a very widely known catalytic reaction. I mentioned it because it does appear at this point as an important reaction just to advance the story. My student at the time was exploring dehydrocoupling, and that is a fundamentally slow reaction, and there's a lot of good reasons for that. Primarily, it's because phosphines are, of course, Lewis bases and coordinate to the catalyst that we would want to do the productive pH activation at. And so my student had a great idea. He said, well, why don't I put in a hydrogen acceptor, and the hydrogen acceptor can presumably accelerate the reaction by preventing a reverse process. And so it's a very simple idea of just having that sacrificial acceptor present. This strategy requires, though, that your catalyst be both a dehydrocoupling catalyst and a hydrogenation catalyst for that terminal acceptor, unless you happen to have an acceptor that will react spontaneously with hydrogen. Turns out that these zirconium compounds are not good catalysts for the hydrogenation with H2. They're actually effective hydrogenation catalysts as transfer hydrogenation catalysts with amine boranes, but we didn't know that at the time. And it turns out that in Mike's reactions, what he had found was hydrophosphonation of the alkene to give both the secondary and tertiary product. And this was effective at ambient temperature. And you may pause and sort of wonder if you missed the minor detail here, why this is so much better when I said it was terrible a minute ago. And the difference is that actually this is now a primary phosphine, and we had been doing our work exclusively with secondary phosphines up until now. Secondary phosphines are in fact the coin of the realm in terms of hydrophosphonation catalysis. These are the most ubiquitous substrates, certainly up till this time. And so primary phosphines are largely ignored in this. And Mike was working on this, and he identified this result, which is very interesting. And I said to him that it's great, but the problem is that this is not good catalysis. You can't be making a mixture product. So I said, please, aim for one thing. And Mike, being very clever, aimed for the easier thing to make, which is the tertiary phosphine product. And in that case, you take the primary phosphine and 2 equivalents of a styrene, for example, and get high yields of the tertiary phosphine product. And I said, that's lovely. But obviously, synthetically interesting is far more interesting is the secondary phosphine product. And Mike was able to develop a very straightforward, mild protocol to make the secondary phosphine product in high isolated yields. So it was a very successful catalytic reaction. It really opened the door for us to be thinking about how to expand hydrophosphonation catalysis. And so there we go. So the question really is where to go on this. And now several years ago, we really sat down and thought about the challenges that were present in the reaction as we had a successful catalyst. And they're threefold. One is substrate, one is catalyst, and one is selectivity. And at that time, we had a fairly active catalyst, so that wasn't the challenge we were going to focus on. And it was substrates that we were thinking about. And there were 2 challenges that were fundamentally present in substrate land, and that is that unactivated alkenes were completely unavailable to this catalysis. And the other challenge is that alkynes were actually a broadly difficult system, and I can explain a little bit more about why they're of particular interest for hydrophosphonation in a couple of minutes. It turns out that for unactivated alkenes, the zirconium was in fact effective at doing some hydrophosphonation, except under forcing conditions. So either we had to be very patient and wait several days, or we had to accelerate the reactions with heatings to give us fairly modest conversions. So it broke through. We had the observation that this was possible, although we didn't have a system that gave us a general reactivity that we would hope for. And that was certainly something we wanted to understand a little bit better. With respect to alkynes, alkynes are available for a reaction that Nakazawa identified in 2012, double hydrophosphonation. That is the sequential addition of 2 phosphines across a triple bond to give the diphosphenoethane. And diphosphenoethanes are, of course, privileged late transition metal ligands. And so this is a very valuable way to potentially make libraries of diphosphenoethane ligands. That original chemistry, that beautiful chemistry, was done with iron catalysts. Unfortunately, it had some limitations, and that was that only terminal alkynes could be used, a lot like our original hydrophosphonation catalysis, and aryl secondary phosphines as substrates. So there's a bigger synthetic space to understand here. And several people have now studied this. We've actually contributed to some of the iron chemistry in this area, and that's not really the subject of what I need to tell you about today. For zirconium, we recognize that terminal alkynes were problematic for us because they would form these terminal alkynyl compounds that would not be reactive. So we recognize that internal alkynes were a more likely substrate for our compounds, and therefore would broaden the synthetic scope of this particular reaction. And so my student at the time, Christine, was able to easily show that we could do single hydrophosphonation to selectively make vinyl phosphines. You'll notice now that I'm starting to show LED light as essentially a reagent in this catalysis, and this is actually important, and I'll get back to the role of light momentarily. substrate scope was broad. We demonstrated that that radicals were unlikely to be in this process with a radical trap. And from there, Christine showed the double hydrophosphonation with a handful of substrates. You'll notice the times are quite long, and that was the norm of this particular reaction anyway. It's just simply challenging to get that second phosphine onto the alkyne. So we've been successful in faster reactions with iron catalysis, but those again are still limited to terminal alkynes. So the reaction is developing, although it is not yet the broad-based way to build diphosphenoethanes as we might hope. The light piece was something that we were very interested in, and so we looked closely at a model transformation, and that's the single addition to this internal alkyne. And if we run the reaction in the absence of external light, then we see virtually no conversion. There's a small amount of vinyl phosphine that appears. When the reaction is irradiated, and this is LED, this is a commercial LED bulb, so we know it is tightly in the visible spectrum, that we see good conversion to the two isomers of the vinyl phosphine product. So the light is essential in this, and our initial photo reactors, I'll put that in loose quotes, look like this, and we as a group had a conversation about the dependence of distance on light, so we started moving these, of course, much closer to the source. The photochemist, the deliberate irradiation of these compounds was a game changer for us. So we can irradiate at ambient temperature with visible light, but visible light cutoff, I'll show you in a minute, is limiting. And so in fact, if we use UV in near UV or far UV, we get remarkable conversions for unactivated alkenes. And so we've really turned on the reactivity. So within 24 hours, we're getting now serviceable conversions for most unactivated alkenes, where we would be getting trivial conversions. It would take days for us to get reactivity before. And I show by comparison here our original hexene reactions, which took itself days at elevated temperatures. The zirconium compounds fluoresce. So this is an image of the compounds under ambient light, and this is an image under near UV irradiation. And so that told us that obviously there was richer photochemistry than was present by simply irradiating these things strictly in the visible. And it's really the photochemistry comes from Christine being a good scientist. She noticed that her conversions were lower when the light bulb in her hood had gone out overnight one time. And so she followed up on that initial observation, and it really led us down this road. UV-vis spectra of zirconium, a model zirconium phosphido compound are shown here. I really draw your attention to 400 nanometers and greater, where there's virtually no features in the UV-vis. It's a small trail of this highest energy transition, and that's the LED region. So we are exciting something, but we're really exciting the edge of that particular feature. And that's the reason why we started moving to other wavelengths of light, is to simply get a better absorption cross-section. So the black lights that we were using, and these were really literally the commercial sort of compact fluorescent black light that one can buy, around that centered around 370 nanometers, sort of fits right on top of this particular transition. The fact that then we could go to much higher energy light back into the far UV is illustrating that cautious rule holds, so we can excite really anywhere on this and then take advantage to much higher photo cross section transitions to get ourselves the reactivity that we're looking for. That dependence on the wavelength was something that we looked at, and it's clearly not a perfect measurement, as you can tell based on the relative lambda maxes of those features. However, as we go up from ambient lighting to LED lighting, we see dramatic improvements in conversion for a test reaction of styrene and phenylphosphine. As we go to that black light, that 370 nanometer centered irradiation, then what we see is even better conversions. And then, of course, in the far UV, we see excellent conversions in limited time. These are tough comparisons too, because the relative energies that are utilized, so the photon flux, are clearly different between these methodologies. We've not really done a very systematic comparison, but the UV vis alone tells us that we're simply going to see a strong dependence on wavelength in terms of reactivity in these cases. At this point, then, we were really perplexed about how this works, what exactly these photons do. This is, of course, a zirconium, formerly zirconium-4 D0 metal. There's very little reason to think that there's exciting photochemistry at that center. And so in collaboration with our colleagues, I show here the UV vis spectrum turned in the spectroscopic way of increasing energy. And through collaborations, we had TD-DFT done, and so modeling of the UV vis spectra is actually quite a good fit. And it turns out that that lowest energy transition is the transition you would think it should be, which is, of course, the ligand to metal charge transfer band, so N to D. And these are the orbitals that are participating based on those calculations. So very much it looks like a p orbital on phosphorus, transitioning electron density to what very much looks like a classic d orbital on zirconium. And so at that point, we were still scratching our heads because an N to D didn't seem to have a lot of value in terms of promoting an insertion-based hydrophosphonation reaction. And that alone was not a big indicator, but when we did calculated structures in the excited state, what we identified was an elongation of the zirconium phosphorus bond. So that excitation, that photo excitation, would take this bond length up by almost an angstrom in the calculations. So a very significant weakening of that bond, and which is non-intuitive, but this acceptor orbital, despite looking almost perfectly like a d orbital, does actually have a significant sigma star contribution to it. And in fact, it is the weakening, the fundamental weakening of the zirconium phosphorus bond that likely leads to accelerated insertion and the hydrophosphonation catalysis that we see. So then, armed with this information of what we could potentially be doing, we were looking for new reactivity. And this was a reaction that we thought would be very interesting because an unconjugated diene now is an unactivated alkene. It's something that's not accessible to conventional hydrophosphonation catalysts, but it should be accessible to zirconium, and indeed that's true. So the reaction of this diene with phenylphosphine provides primarily this ring, although we do observe this linear product as well under the conditions shown. And so we wanted to verify, in fact, what was happening, which was what we would think, that is, it's a sequential hydrophosphonation at the terminal alkene followed by a ring closure event. So independently, we prepared the intermediate compound, which then we could subject to hydrophosphonation catalysis with our zirconium, which gave the ring closed product under those conditions. Interestingly, we found that there was some spontaneous ring closure as well. So this reaction does seem to proceed on its own without zirconium, which is surprising. And indeed, we found that to be particularly interesting because this terminal zirconium final, this unconjugated final derivative of zirconium is interesting in that it has been the subject of hydrophosphonation, ring closing hydrophosphonation before. But the product in those cases, hearkening back to some of Tobin Marx's early works, and then more recently, some of Ruth Webster's innovative iron catalysis, it just provides the different regioisomers, is the 2,1 insertion versus the 1,2 insertion. So there are interesting differences in the reactivity of our photoexcited system versus the conventional thermal systems. But the more important part is that these catalysts require preformation of this compound versus taking what is a broader array of potential unconjugated dienes and primary phosphines. And some, though, the idea is that we can take this and use it to build new molecular structures, particularly phosphorus-containing heterocycles. So that's an interesting set of results. And so then the question is, of course, where are we going to take this? And I showed this slide before of the challenges in hydrophosphonation catalysis. And thinking broadly about the availability of elements, this idea that I brought up before, zirconium is relatively abundant, but of course it's under stress. And so we really want to be at the most abundant transition metals possible. So we want to be thinking ideally about 3D elements that we could be using. And so the first thing along that path, though, of course, is to go back to the reaction that I showed you at the beginning for hydrophosphonation, which was this hydrophosphonation of terminal alkynes to give mixtures of vinyl phosphine products. In the original catalysis, it was elevated temperatures, long reaction times, and relatively high loadings. When we can irradiate at ambient temperature for the same time period at much lower loading, we can get better conversions. So we were feeling better about the reactivity that's possible, and it was nice to compare ourselves to what we could do. And those reactions then in general allow us to start to explore other substrates with the secondary phosphine substrates. Remember, I completely diverted by using primary phosphine substrates, so I'm ignoring a broad class of phosphine substrates in these reactions. And for styrenes and for Michael acceptors, which are the most common hydrophosphonation substrates, catalyzed or not, our conditions are excellent. Conversions are excellent with zirconium under photolysis with secondary phosphines. For unactivated alkenes, they're still not good, but in fact, we have access to a much wider array of both phosphine and unsaturated substrates. And this is doubtlessly for the same reason that it worked for the phenyl phosphido derivative, and that is the UV-vis spectrum of the secondary phosphine phosphido compound is virtually identical. So not inserting is of course a possibility. So again, this is the same reaction I showed you a minute ago, and I alluded to hydroarsenation. And while we're not talking a lot about hydroarsenation, it is a reaction that comes up now and then in our lives. And so the arsenido derivative here, I show a crude UV-vis spectrum of the toluol derivative of zirconium. It can undergo hydroarsenation, and in fact, we see modest to good conversions for styrenes and better conversions for Michael acceptors. And for unactivated alkenes, there's no conversion whatsoever. And this is arguably a surprising reaction. We would think that the zirconium arsenic bond should be fairly weak. It should certainly be longer. And so there's some reasons to believe that this should be a more facile insertion, even though that's clearly not borne out. But what we did observe is that for the styrene derivatives, that we saw only reactivity under photolysis. So it's not just that this is a more facile reaction. That's absolutely not true, because the control reactions in the dark don't go. But what we did observe is that for a proper Michael acceptor, we saw accelerated reaction in the light. So this is clearly promoted by the photocatalytic pathway that I mentioned before. But in that case, we see reaction regardless of light, suggesting that in fact for arsenes, for hydroarsenation, we have both insertion-based pathways as well as a nucleophilic attack at the zirconium-based arsenido. The photons, the photolysis is something that extends beyond the zirconium geometry. And so there's been some nice follow-up zirconium catalysis reported a few years ago. So there's a handful of different ligands that were utilized. And I simply draw your attention to this phenoxide derivative because it is geometrically different than our triamidoamine zirconium compound. So now we're talking about same metal, different geometry. And in this case, we can see substantial acceleration by irradiation of these compounds that were reported by others in comparative times. And so it's really about activating its zirconium. It's not special to that ligand set. We were looking at, I mentioned again, a different reaction. It was deliberate to talk about that alpha phosphinidine elimination. This is an example of that. So CP iron biscarbonyl methyl, so what's known as FIP methyl, will catalyze the transfer of phosphinidine from phenylphosphine to conjugated dienes like 2,3-dimethylbutadiene to give phosphorophosphorines. So that reaction was successful, and we were curious about light in that particular transformation. So it's a different reaction, but the light may be important. It works in the dark, so it's clearly not photo dependent, and 65 degrees is the standard temperature for that particular transformation. We were curious though about whether photolysis would displace that thermal reactivity, and in fact it does not. So under ambient temperature with irradiation, FIP methyl does not do the same phosphinidine transfer that we were looking at a minute ago. However, there is very rich photochemistry associated with these CP iron biscarbonyl fragments, and I show a summary of that is borrowed from the late Thomas Bitterwolf's excellent review on the photochemistry of these systems. And really, a lot of that can be driven to the 17 electron FIP radical. And so rather than sort of thinking about what might be done with our reaction, we thought deliberately about generating that radical and what could happen there. And so again, we took the FIP dimer, which is actually the easiest way to get to the 17 electron compound under visible light irradiation. And that does not do phosphinidine transfer, but what it does do is hydrophosphonation. So what we have observed, and simply for the length of time available, we found that FIP dimer actually is activated in solution, and it appears through a cooperative process. pH activates at the phosphide, so presumably we're generating an equivalent of the iron phosphido and the iron hydride. The FIP hydride is known to decompose back to FIP dimer, so that makes a clean loop to continue to reactivate catalyst, and presumably then the FIP phosphide can undergo an insertion reaction and provide the hydrophosphonation product. And so that reactivity was interesting. This is therefore, and the photolysis is important for the pH activation step, not for the overall turnover. So this is photoactivated chemistry, not photocatalytic. In that process, as we were thinking about that, we were interested in this double hydrophosphonation reaction. I mentioned that Nakazawa had identified that originally, and so I'll show Nakazawa's reaction here again. We were thinking about this reaction, and so FIP dimer is not what Nakazawa was using. He was actually using that FIP methyl. And what we identified in this reaction is that under irradiation, we were now seeing the chemistry turnover in a couple of days, when versus 3 or 4 days for Nakazawa's system. And then if we ran the reaction thermally, we were seeing conversion in about a day. And the thermal reaction actually is simply faster than the photochemistry to generate the 17 electron species. And so there's no reason to think that anything is different here, that we're not getting pH activation via cooperative processes, 217 electron iron intermediates. In Nakazawa's case, there's liberation of, or proposed liberation of that methyl after insertion or after migratory insertion with the carbonyl ligand. In that case, the reaction appears to be slow based on coordination of the intermediate to the iron. Because both carbonyls are retained at iron, we think that's the reason why this catalysis is substantially faster than the original. And just as a reference then, so now what we're seeing is fast conversion to the secondary system. We also can build the primary systems, which we could conceivably functionalize at phosphorus. And so there's now actually a whole stable of these compounds, and they're relatively accessible. So styrene is now the substrate of choice. So when we really started in on this chemistry about 10 years ago, it was Michael acceptors. People would compare those routinely. Most of the catalysts were late metal catalysts. And so the field is really driven to styrene as the benchmark catalyst. And so I show that here just to compare some catalysts that are known. So for zirconium derivatives, under 360 nanometer irradiation, within 90 minutes or less, for the secondary phosphine, we see complete conversion into the hydrophosphonation product. The FIP dimer I mentioned a couple of minutes ago, that takes about a half a day to go to about 100%. And that's actually really a function of generating enough of the 17 electron intermediate. For the zirconium, it's really a function of how many photons will that compound absorb at that wavelength. These are clearly, relatively fast compared to some of the conventional systems. It's not ideal yet. And so most recently, we've identified a very simple copper derivative. So copper ACAC, many of you have this on a shelf somewhere. Turns out that if you can add copper ACAC to this reaction, irradiate it in the near UV, and in fact, the turnover is incredibly fast. And so within about 20 minutes, you get complete conversion for styrene and phenylphosphine. I'm not big on tables. I could walk through this and talk about some of the relationships. It works with styrenes. It works with unactivated alkenes. I show a bunch of unactivated alkenes here. It works with activated alkenes, Michael acceptors. It works with alkynes. it's an incredibly active catalyst. You'll notice the times measured in minutes. For some of these tougher substrates, it's measured in hours. It works for primary, it works for secondary phosphines. So copper is, it is the most available catalyst you're going to find. It's the one you can just simply pull off the shelf. It self-activates. So it is really the new vista for simplicity in terms of making this a synthetically accessible reaction. What do we know about this? So we're midstream in mechanistic studies to understand better the copper and then how to optimize that particular catalyst. And so what we do know is that the copper reacts with phenylphosphine under reaction conditions to simply protonate off the ACK ligand, which is telling us something important that's unique to certain kinds of reactions with copper. The really important observation is the 1,2-diphenyl diphosphine. And so this coupled product is telling us that actually we're going from copper 2 to copper 1. And what I can do is illustrate for you here the formation of the diphosphine here, the 1,2-diphenyl diphosphine. This black line is the theoretical maximum. So we peg ourselves exactly to making the one equivalent. And we also then track rapidly with making 2 equivalents of ACAC. So really what we're thinking is that the copper 2 is being sort of sharply converted right into copper 1, and it's copper 1 that's doing the work. So that's not a surprising observation with how a lot of copper catalyst works, but it's very clean in the way in which phosphorus can support that redox chemistry. And then further, the light obviously matters. So if we do this in the dark, we see considerably slower transformations. And I also show a light dependence here. So ambient lighting works quite well. So basically you can set this reaction up and run it. It just takes a bit of time to get full conversion. And so times in minutes, these are still not bad. If we deliberately run the reaction in the dark, there is some background reactivity. So this will thermally convert at ambient temperature to an extent. It just won't be very effective. And then, of course, LED and then UV light accelerate this. So just direct irradiation. So increasing the photon density essentially with an LED bulb or increasing that energy with a UV bulb. And so you can make the choice about how much you would like to prompt this reaction, but it will simply turn over. We can deuterate at the phosphine, and we see very selective deuterium incorporation at the product. So that works exactly as expected. The deuterium is a little bit more complex on the ACAC, but that's a slightly different problem. We see an inflection when we do Hammett studies. So electron donating substituents on our substrate phosphine give us one dependence, whereas electron withdrawing groups give us the other, and same thing with the primary. The inflection to us is an indication that we're seeing a change in mechanism. And I'll explain that actually in the cycle that I have proposed here. So as I was explaining before, copper ACAC in the presence of phosphine protonates off ACAC and forms tetraphenyl diphosphine, which gives us a copper 1 intermediate. There's doubtlessly some more complicating chemistry here because there is something that supports copper. We're not just making copper 1 free floating in solution. Critical to that is some kind of pH activation event. I sort of loosely draw this in some way, and I only draw it because there is the possibility for a copper hydride versus a copper phosphide insertion process that prompts this reactivity. And in either case still gives us the regioselectivity that we would expect for the product. This is the insertion-based reaction. This is essentially the required reaction we need to activate the unactivated alkene substrates. The reason I mentioned before that's possibility of having differential mechanisms is that the copper phosphido simply is activated as a nucleophile and can attack an electrophilic unsaturated substrate. And that's why we see the difference, and that's why we see acceleration with the electron withdrawing substrates. And so we're not fully there on mechanism. This is a work in progress, but I think it is consistent with the data that we have, and it is certainly a good starting point for us to continue to understand this catalysis, which is itself remarkable. And with that, I just want to summarize. So as I mentioned earlier, we weren't really good at this reaction, and we let it go for a little while, which I think was probably the best thing as opposed to hammering at it arbitrarily. And from there, what we really discovered, and that was the most critical part, was that photolysis was essential, and understanding, in fact, that there was the ligand metal charge transfer that drives the reaction taught us a great deal about how to turn on this. And then armed with that photons really can do something, we're able to discover inexpensive, simple, available catalysts for this transformation. And overall, I think that supports this idea that photocatalysis and photoactivation are going to be very important for PC bond formation in the future. With that, thank the group again. The same picture and some folks are named here. This is primarily a National Science Foundation funded project. This is the University of Vermont's campus in the back, and we are actually on Lake Champlain. You can kind of see it in the back. Lake Champlain is a relatively large lake in New England, and in fact, it's old, and there's a lot of legends that exist for a long time. And so if you ever come to Vermont, you're all welcome to when it's safe. You might actually see our lake monster, Champ, and so there's the occasional blurry photographic evidence. Thank you to the speaker, to the organizers for the invitation. It was a delight to share some of our chemistry, and I'd be happy to answer questions.
What? No one is asking questions. Just thank you very much, sir. Thank you very much for picking up this event and providing a perspective. Thank you for sharing tips with us. Looking forward to meet you again next time.
Yes, sounds good. Thank you.
Hello? Hello, can I speak? Hello?
No, we asked Dr. Gakik Shamanwaniam from National Polytechnic University of Armenia, Department of Microelectronics and Biomedical Device to start the presentation.
Okay, thank you very much. Can you hear me? Yes, ma'am. Hello?
Yes, sir, you can start your presentation.
Can you hear me? Hello?
Yes.
Can I start?
Yes, you can start your presentation.
Okay, thank you very much. The title of my presentation is Two-Dimensional Material Nanostripe Array Films consisting of self-assembled quantum dots formed by simply rubbing. Okay, so I'm going to speak about graphene and two-dimensional atomic materials. Then I'll continue to speak about the main problem of synthesis of two-dimensional atomic materials, their solution, and then I'm going to speak about our patented substrate rubbing technology, rubbed nanosite product nanostripes, about the rubbing process, rubbing mechanism, and the rubbing conditions. So, and then I'll present a few examples of rub samples, and then I'll speak about heterostructures and the advantages of the technologies. So what is graphene? Graphene and two-dimensional materials. Graphene is a single atomic layer of graphite. So it is the thinnest material at the moment and the mechanically strongest and at the same time flexible, the highest electrical and conductivity conductivity. So there are different methods for preparation of graphene and two-dimensional materials, which we can divide into two groups: a top-down approach, and the second one is bottom-up approach. Top-down approach methods includes micromechanical exfoliation, liquid phase exfoliation, chemical exfoliation, and so on. And the bottom-up approach includes CVD growth on metal surfaces, epitaxial growth, and so on. And so I am going to speak about the main problems of the synthesis. So as you know, the first method is micromechanical exfoliation method, which allows to get graphene flakes, but the micromechanical exfoliation is simple, but it has low yield, messy, and not suitable for mass production. The exfoliated graphene flakes are small in size. And the second method is CVD growth. This epitaxial growth is high temperature process, and it is difficult to control the morphology and absorption energy. And the grown sheets has grain boundaries. So it's better to develop an easy method for obtaining high quality graphene directly on the substrate without using chemicals, high temperature, and sophisticated devices. So that's why we need simple, cheap, and fast methods, which includes graphite-based raw materials. So the methods are rubbing, mechanical thinning, shear exfoliation in liquids, wet ball milling, roll to roll, and so on. So the main problems of synthesis are that the processes are long-lasting, sophisticated, and non-direct. They use toxic chemicals, high temperatures, and expensive equipment. So what can be the solution? So recently we suggested a new technology, which we call substrate rubbing technology, which is cheap, easy, short-lasting, ecologically clean, high productive, universal technology for mass production of cheap, high-quality, big lateral size graphene and for production of two-dimensional materials. So how to make graphene and two-dimensional materials which are suitable for mass production. So here is the substrate rubbing technology in which we decided to avoid Scotch tape method and use, instead of Scotch tape method and pencil, we use two substrates. So, and during this process, rubbing process, we are not using any templates, techniques, and so high temperature chemicals and sonication. And more interestingly, we can realize this process, rubbing process by hand. Oh, so the substrate rubbing technology is an extremely simple, fast, cost-effective, chemical-free, transfer-free, reliable, highly productive, and industry scalable method, which allow us to get unique two-dimensional atomic nanostrips. And these two-dimensional nanostrips are reported for the first time by us in the following literature. And so this substrate rubbing technology allows obtaining two-dimensional atomic material nanostructure with various nanoarchitecture of parallel aligned nanostripe trace films with tunable sizes, shape, morphology, density on any rigid and flexible inorganic and organic substrates. These nanostripes can be obtained manually or mechanically by rubbing layered bulk materials on different substrates at atmospheric pressure conditions without using any template and technique. So here you can see the process of rubbing process. The method compromises putting pristine bulk layered material such as graphite between two solid substrates and rubbing the substrates against each other. As a result, multi-layer nanostrips appear on the surfaces of two substrates. We did, after further rubbing, dots eliminated and multi-layer nanostrips converted to few layer and then monolayer nanostrips. So, okay, let's to see the optical images of this. After few rubbings, bulk dots and nanostrips appear, and After further rubbings, bulk dots are eliminated through shearing and converted into multi-layer nanostripes. After further rubbings, a dense network of nanostripes and then a sheet of nanostripe is formed on the substrate surface. And you can see below the conditions of the rubbing, I mean the pressure and the rubbing cycles. And so two-dimensional material nanostripes, as I told you before, are reported for the first time, which are mono, few, and multiple atomic layers of exfoliated flakes organized in self-assembled narrow bands of nano-sized quantum dots. So as you can see, these nanostripes can have different shape, different sizes, morphology, density, and shape. And besides, it's possible to obtain 2D sheets with different sizes of nanostripes, 2D heterostructures, as well as the powder of the of these nanostripes. So here you can see a few SEM images of nanostripes and sheets of nanostripes, and below you can see the you can see graphene layer consisting of nanostripes. Here, the first one is optical image, and the second one is SEM image. The pressure is 200 Pascal, and the rubbing cycles 500. Besides, we measure Raman spectra of these nanostripes, and you can see from 1 to 5 are the spectra from bulk graphite nanostripes to monolayer graphene nanostripes. And the number of rubbing increases with the increase of the number of the spectra, and then you can see that we observe new peak, which is in 1,400, and which we want to explain the origin of this peak. Here you can see AFM images of these nanostripes at different scales. We measure also IV characteristics of these mono and multi-layer graphene nanostripes, and you can see that there is big difference between graphite and graphene nanostripes of IVs. Rubbing mechanism, so you can see TM image, and you can see that clearly. You can see the structure of graphene stripes, graphene sheets. So the rubbing process is very simple, extremely short lasting process. It's about 150. It takes 150 seconds, and here you can see the rubbing conditions. So we use different substrates, we use different powders, and also different rubbings are carried out in different directions, numbers, pressure applied to the substrate, rates. And rubbings are carried out manually, continuously, or subsequently, horizontally, or vertically at atmospheric pressure conditions. So here there are a few examples of substrates, and with different hardnesses. You can see here, here we use different substrates like silicon, carbide, sapphire, silicon, glass, cobalt, plastic, wood, paper. We use also here different powders. We use small amount of powder and big amount powder. In any case, you can see a different nanostripes, and there is transition. If there is transition from multi-layer nanostripes to mono or few layer nanostripes. Rubbings are carried out at different distribution of powders, and so you can see uniformly distributed and non-uniformly distributed powder, and also rubbing mostly on 1 or 2 edges are carried out as well. So we use different applied pressure to the substrates, and also you can see that the rubbing also depends on the applied pressure. Nanostripes with different form and sizes, you can see on these images. So the sizes of the rubbed nanostripes are the following. The upper limit of nanostripe length is millimeter size or more, and the nanostripe width changes from few tens of nanometers to millimeters. The size of the shape of the wrap sheets depends also on the size and shape of the substrate. Here also we carried out for boron nitride powder rubbing, and you can see here we also get the same behavior. And also here you can see Raman spectra of hexagonal boron nitride nanostripes. And also you can see here the transition from bulk boron nitride powder to monolayer boron nitride monolayer nanostripes. So here you can see 2D heterostructure consisting of nanostripes of graphene, the thick lines, and also thin lines which illustrates hexagonal boron nitride. So from this you can see that graphene nanostripes are very similar to graphene nanoribbons, and so you can see the sheet of nanostripes in the below image. So this technology we patented. Here you can see the Spanish patent. Then we extended it to EPO, WIPO, and also that we published our paper in the following in the Translational Materials Research Institute of Physics journal. So the substrate rubbing method is an extremely simple, extremely fast, cost-effective, transfer-free, chemical-free, reliable, highly productive, universal, industrially scalable method, which allow obtaining to the dimensional material unique, self-organized nanostripes with different sizes and density in plane aligned nanostripe sheets, hybrid heterostructured with almost perfect plane interfaces. They are dispersion in liquid or powder. So I want to mention that we are open for collaboration for theoretical calculation and or simulations, or also we are interested in functionalization of these nanostripes, which can be used in as membranes, filters, coatings, composites, energy storage, smart materials, electronic textiles, etc. And then I want to thank my colleagues, Professor Lopez Quintela and Carlos Vasquez from University of Santiago de Compostela, and Arek Shmaunian from Yerevan State University. Thank you for your attention. And I want to thank the organizers of the conference for this interesting conference.
Yes. Any questions? Any questions to Dr. Gagi?
Yes.
Any questions? No other questions, sir.
Okay.
Yes, thank you very much, sir.
Okay, thank you.
Thank you very much for speaking up in this meeting.
Thank you very much.
Yes, and providing a unique perspective. Thanks for sharing your tips with us. Looking forward to meet you again next time. Yes. Next talk will be, the last session of this session will be Dr. Iva Rizik. We welcome Dr. Iva Rizik to join the event and start presentation. Yes, just you can play your PowerPoint presentation from your side.
Hello everyone. I hope you can see my presentation and hear me good. Is it okay? So first of all, I would also like to thank you, the organizers, for your kind invitation. It is my great privilege to be here to listen to your presentations and to show you the research work that is done here. We are contacting you from Croatia. This is a country in Europe. And our group is focused on finding the most efficient materials that are active against microorganisms which are resistant to antibiotics. We will see today why this problem is very, very important. So we have problems. because today the classical methods in which we use antibiotics in hospital treatments are not effective. Many strains of microbial infections are facing major problems because those microorganisms are becoming resistant to most commonly used antibiotic treatments. So a few years ago, in 2014, the World Health Organization organized its first global report on antibiotic resistance, and they have presented data from 114 countries. As you will see, this problem with antimicrobial resistances is the major problem and the serious major world threat to public health before COVID-19. So given the fact that this has been confirmed, the World Health Organization also opened a call to produce different preventive materials and to develop new materials and procedures in which we could prevent such infections. So what is proven is that we have correlation which exists between the length of stay in hospitals for patients with infections and the harmful microorganisms attacks. Various materials that those patients and nurses and doctors are coming into contact include bedding, towels, sheets, bandages, catheters, and other hospital equipment. And all of these materials can present source of danger if they're not sterile. An especially dangerous bacteria that is the focus of our research is so-called superbacteria. This is Staphylococcus aureus or MRSA, which is resistant to a wide range of different antibiotic-based penicillin drugs. So what are the facts? You will see that by some predictions, by 2050, from the infections caused by these antibiotic-resistant bacteria, more people could die than from cancer. And only in Europe, 25,000 deaths per year and costs over $1.5 billion are associated with resistant microorganisms. So this number of deaths is greater than the sum of deaths caused by AIDS, tuberculosis, and viral hepatitis together. And for COVID, we don't have data yet. So our project and our group is focused on finding the solution. So what do? We are using nanoparticles. So you know that those particles are in range from 1 to 100 nanometers. And they're so small that they can easily interact with proteins, DNA, and viruses, as you can see on this slide. Moreover, they are much smaller than the cells, also microorganism cells. So in this photography, you can see how these nanoparticles can really easily penetrate through the cell walls. And it has been reported, and the photographs can be reported, that pits and pores can occur in this bacterial cell, which actually leads to cell death. So we can kill these microorganisms which are resistant to these penicillin drugs. Our project therefore is focused on investigation of nanoparticles which are active against specially designed microorganisms, which are MRSA and MSSA. Those are these methyl-resistant Staphylococcus aureus, in protective coating for different materials that will be used in hospitals. So what we do, we produce antibacterial coating, we test those materials, but we also produce the polymers for beneath the coating, which are different biodegradable polymers. We use natural biodegradable polymers, but also man-made polymers. And in the end, we apply different methodology to investigate those nanoparticles. So we're trying to develop chromatography procedures, spectroscopy procedures, and microscopy procedures in order to see nanoparticles on materials and afterwards to test these in focus with antibacterial testing. The first step in our laboratory is how to prepare this material, polymer, that is coated with nanoparticles. For this, we use Largescale functionalization methodology, also called deep coating, in which we have these different chemicals which we mix with nanoparticles, put in solution, and then our polymer is dipped into and slowly put out in order to have the result, which is actually homogeneous layer on large surfaces. This procedure has many advantages because we can produce homogeneous, unified, and flat coating. The temperatures that we use are rather low, below 100 degrees Celsius, It's very flexible projects, and we can modify really large surfaces. The second step is to develop a chromatography procedure in which you will be able to detect the metals which are present in the nanoparticles. And why did we choose thin layer chromatography? Because until now it was not tested yet. And this is proved to be efficient, fast, and simple methodology in which you can analyze metal ions. Of course, there is ion chromatography, but in this procedure you need columns and instrumentation. And here you don't have problems with the really problematic samples. So in modern materials, it's possible to detect wide range of different analytes and material coatings, which define spatial usage properties in samples. So, as you will see, we, during the application and development of this chromatography procedure, we investigated 31 different stationary phases, which was combined with prepared cellulose, silica gel, polyamide, and alumina oxides. We created 19 mobile phases and varied different organic solvents like acetonitrile, acetyl-acetone, butanol, triethylamine, ethyl diamine tetraacetic acid, hydrochloric acid, water, and others. And as metal ions, we combined the experiments with 64 different metal ions. The bases were polymers, two kinds of polymers. The first was these 3D printed polymers, which can really easily be functionalized with nanoparticle coatings. And afterwards, you can make all kinds of shapes, so you can produce catheters, consumables, coatings, and decks. And the second kind of material that we are modifying is actually this cellulose, textile, woven, or knitted materials. In this picture, you have our sample of crucible coating. So how do we do man-made polymers? First, we have an idea which you are creating in a computer program, then you model it in another computer program, and then from this model to product, there is only one step, which is called additive technology or 3D printing. When you produce this polymer, which is actually the carrier for coating, then we use solid gel functionalization, and the result, we need to confirm So in this picture, you have the red line, which is actually our sample before modification. And then we have blue and black lines after modification. And you can really see that around 900 centimeters, we have epoxy groups who have occurred. Around 1,100 centimeters, we have groups with silica. And here around 2,870 centimeters, we have conversion of metopsy groups by precursor polymer. So this is the result of this chemical modification of solid gel process methodology, and this is actually how we can prove that we have really stable coating on our polymer. Second step is to use microscopy. We use scanning electronic microscopy equipped with EDX detector. So firstly, with this strong microscopy, we take a picture of a sample on which surface you can see small nanoparticles. And then we apply this EDX detector to see which element is present, which nanoparticle actually it is. And you can see here the result for silver nanoparticle. So when we have proof which nanoparticles are present on the surface of polymer, we can try to see what is extracted. So for this, we are currently in process of development of chromatography procedure in which we test 64 different metal ions with different, as you can see, stationary phases, different mobile phases, and we are monitoring the ranges where the spots of the samples are occurring on a plate, and this is ongoing research for now. So what we can measure actually is retention factor. This is actually the place where a particular metal ion has moved when it's carried by a mobile phase on the plate. And the last, but maybe for this focus, the most important part of our investigation is actually how to test the antibacterial effects So we have 3 different methodology. Here you will see the results of diffusion and microdilution methodology who are done in vitro, but also we are trying to develop real-time new method to see really in time how this material is behaving. So this work and this presentation is focused on material on MRSA. So these are Staphylococcus aureus, metal-resistant microorganisms. Here in this picture, you can see how it's really efficient and how we have positive results with nanoparticles. The focus is on silver zinc oxide nanoparticles, but we have tested also 10 others. And with titanium oxide, we also have positive results. And preliminary results on different Staphylococcus aureus that are not MRSA and MSSA have showed some effects, but then you have this table, the result really produced on MSSA and MRSA microorganisms. And you will see that we really have positive effects against these really problematic microorganisms. So what did we see during our experiments? So we saw that this is zone of inhibition. This is the area where microorganisms are actually dying due to presence of nanoparticles. Really occurs on this, and it's really significant. And the best results we had with zinc oxide nanoparticles, which was followed by silver nanoparticles. What also did we saw? We were varied with different concentrations from 15, 10 to 20% of nanoparticles. And with zinc nanoparticles, we have better results with higher concentrations. But it was really interesting, which is now ongoing research, to see how the size of nanoparticles with the same concentration is influencing the results. And we have some really contradictory data because in our experiments, smaller nanoparticles are more efficient than bigger nanoparticles, but we still need to prove this. So for MRSA microorganisms, you saw the results of silver and zinc, and titanium oxide is 80 times worse, so it's actually not a good goal for our future application. What did we do? So we took tests in different hours, and as you can see in this graph, after 6 hours, a really strong effect starts. So after 6 hours of exposure, all these non-wanted microorganisms will be killed on the surface of materials, so which actually proves that our materials with such coatings are excellent preventive medical materials who can be thoroughly investigated for this purpose. So what can we conclude for this short presentation is that nanoparticles of metals and metal oxides really have direct antibacterial effect with time, and for this reason are excellent actually coatings for medical materials. What we saw also is that metal nanoparticles influence MSSA and MRSA through interaction with microorganisms, and this interaction was dependent on the size of nanoparticle, on concentration of nanoparticle, and also on chemical composition of nanoparticle. Therefore, our materials can be seen or foreseen as protective coating, masks, gloves, and all other materials more important in hospitals. So this is really one global and interdisciplinary investigation. This is performed on a project ABA Medica, who is financed by Croatian Science Foundation, for which the whole group is really, really grateful. And some members of the team are present here on this photo. Unfortunately, not here present with me today, but I'm very grateful because we have colleagues from 3 or 4 different faculties here in Zagreb, from hospitals, and from some research institutes. So these results could not be investigated or discovered without the cooperation. So thank you all for listening to this presentation. If you have questions, actually, you can ask or maybe write in the chat.
Any questions? Any questions to Dr. Iva Rezik?
Thank you.
Any questions? Yes. So almost we have completed all the session speakers during the day 2 of the conference. Madam. We have two more speakers. They are not responding to our mails. Thank you very much to all the participants. Thank you very much to all the participants, those who joined this webinar chemistry event during this period, during having different time zones. Our most sincere thanks to all keynote speakers, plenary speakers, delegates, general collaborators, media partners who had joined from different destinations around the globe for their support and cooperation. Let us thank speakers who have responded so well to our invitation to participate in this conference. We have received several papers which will form the basis of our discussion in the various sessions. Let us thank you all for associating with this conference by your presence. A special thanks to Program Manager Ms. Lara Christian for her continuous effort in putting us together under one platform in this online event. The keynote lecturers from day 2, especially Dr. Anil Ramdas Bari, as well as speakers, plenary speakers, Dr. Shuji Ogota, Dr. Sabu Thomas, Dr. Baktanga, Barkbidis, Dr. Ivarizik, as well as Dr. Gaigi Shamonamani. Especially be thankful to Dr. Wesley Lutsik, the keynote speaker of the day 1 normal session speaker, Dr. Geoffrey Mitchell, as Ruben Mas Baleste, staying for today of the sessions. And especially thankful to day 1 speakers, Vijay Chelvendraj, Osman Adiguzal, Juana Dupici, Tingo Gua, and as well as Dr. Cyprian. We will send you officially through electronic certificate as well as electronic book. Finally, we extend our appreciation to each of you for the participation in this online conference. Thank you for your patience. Thanks for attending our webinar. Hope as the theme of the event, scientific research approach in chemical and nanoscience, we hope you enjoyed it. If you have any questions wasn't answered during this live event, you can share through mail within the next day or 2. We will send you officially through mail electronic certificate as well as electronic handbook. If everything goes well in 2021, we hope we all join in physical event on same topic, Chemistry Congress 2021. Thanks again. Have a nice day. This is signing off, Madhu Bhupati.
Many thanks, dear moderator.
Thank you very much, sir, for being patient.
Thanks a lot to you and your team, everybody from your organizing committee. I wish you excellent health, good luck, and success. Okay?
Yes, sir. Thank you. Thank you for your patience, sir. Have a nice day.